Writing large binary patterns, for instance of 32 bits, is pretty tedious. Let's look at a condensed way to represent binary patterns using base 8 or base 16. Now, we'll be doing conversions between 3 different numerical bases, bases 2, 8, and 16. But before we do, it's useful to consider something we instinctively do with base 10 numbers that relates strongly to how we'll do those other base conversions. While we think that we count in base 10, in a certain sense we actually think in base 1000. And to see what I mean, try reading aloud the following number over here. Now, if you did that, you probably said 123,456,789. We even add commas, or periods in some nations, to separate the digits into groups of 3. Importantly, you didn't announce each place value when you said the number, or even when you think about it. No one says or thinks 400,000s, 10,000s, 6,000s. Instead, we break the number at what we might call benchmark place values, such as the 1000s place. And we think of the digits to the left of each benchmark place relative to that place value. So we see the 4 and the 5 in our sample as being the 100s and 10s place relative to the 1000. And the digits 456 collectively tell us how many thousands we have. Same thing goes for the millions place, of course. We think of the 3 as how many 1 millions, the 2 as how many 10 millions, and the 1 is how many 100 millions, 123 million. We're actually describing our decimal number in base 1000. Now, what would be the place values in base 1000? Well, they'd be powers of 1000. We'd have a ones place, and then a thousands place, and then a millions place, and so forth. And these are exactly the benchmark place values that we use to break up a decimal number. Indeed, we have terms in English and in many languages for those benchmark place values: thousand, million, billion, trillion, but not for most other place values. What this shows is that you can convert between certain bases by choosing benchmark place values in the smaller base and grouping digits around those place values to arrive at the larger base. Now, for this to work, the larger base has to be some power of the smaller one. 1000 is 10 to the third power, for instance. And we convert from base 10 to base 1000 by grouping digits by 3s. As long as the larger base is some integer power of the smaller one, the system will work. If we chose to, we might have grouped decimal digits by 4s, made up words for each 4 powers of 10, and counted in base 10,000. Indeed, one Chinese numbering system does exactly that. So, how does this apply to binary values? Consider the 9-bit binary 101, 011, 110. Let's write it with commas grouping every 3 bits, just like we do for decimal values. Now we have 101, 011, 110. Here's the first in-lecture question. What are the place values of the bits immediately to the left of the 2 commas? And to which higher base do those place values correspond? The answer here is that the place values are the 8's place and the 64's place. They're the place values above the 1's place in a base 8 number. So we can view this 9-bit binary number as a 3-digit base 8 or octal number in a fashion very much like what we did for base 10 and base 1000. For instance, bit 4 here can be viewed as the 16's place or as the 2 8's place, and so forth. The diagram now shows this interpretation for all 9 bits. These are the 4, 2, and 1 1's places. Here's the 4, 2, and 1 8's, the 4, 2, and 1 64's. And then we can use a single digit for each grouping in base 8, something we can't do for the base 1000 case, because the highest value we can count with 3 bits is 111, or 7. So our sample value translates to base 8 thus. That's 101 or 5 64s, 011 or 3 8s, and 110 or 6 1s. So if you understand what we're doing, here's an in-lecture question. Translate the following binary number into octal. And if you had a chance to think about that, let's start by just grouping it by threes. And what we should come up with then is 1, 7, 6, 3, 4, 2, 5, 6, 0, 3, and 4. So why do we care to do this? Well, as discussed earlier, sometimes you want to put a particular pattern of bits into an integer. The numerical value is incidental, but you have to assign some number into an int in order to get the bit pattern. Assigning an octal number is more convenient than assigning a decimal because once you get the hang of it, it's very easy to translate a desired bit pattern into an octal value and vice versa. Most programming languages, including ARM assembly, let you express a constant in octal for this reason. You do this by adding an otherwise meaningless 0. 042, for instance, is octal 42, or decimal 34. We introduced octal first because of its natural connection with the 3-digit groupings in base 10, and because octal values use the familiar digits 0 through 7. But octal has two problems as a base. First, it compresses only 3 bits into each octal digit. And second, integers come in sizes of 8, 16, 32, and perhaps 64 bits. None of those sizes are divisible by 3. So the most significant octal digit is always encoding only 1 or 2 bits, which is somewhat inelegant. What would be better, and what is more common in assembly, is to use 4-bit groups, breaking the binary number up that we just dealt with thus. And an in-lecture question: what are the place values of the bits immediately to the left of the commas, or at least the lower ones, in this case, and what number base do they correspond to? So the answer there is going from right to left. This is the 16's place. There's the 64's place, the 256's place. Here's the 4096's place, and the 65,536's place right up there. These are powers of 16. And they correspond to base 16 place values. So we can also convert to base 16, or hexadecimal, often abbreviated to just hex, by reading each 4-bit group as a base 16 number. We'll annotate the diagram here to show how we're interpreting the bits. Bits 8 through 11, for instance, right here, are interpreted relative to the 256's place, and they show how many 1s, 2s, 4s, and 8s of 256's there are. In the diagram example here, that's actually 8 plus 4 is 12 256's. Grouping by 4 bits crams more bits into each digit in the larger base, and 4 divides evenly into every integer bit size in common use. This is good. What is bad, however, is that we have to count up to 15, the highest possible value in one place in hexadecimal, using single symbols. We only had to count up to 7 per place value in octal. The decimal system we're used to only supplies digits up to 9, so the universal convention is to use letters A through F for the values 10 through 15 in hex. Hexadecimal values are combinations of the standard digits and these added digits. So the binary value from the diagram translates into 7. 011 is 7. 1110 is 14, or E. And then 0111 again is 7. And 0001 is 1. 1015. But here 1100 is 12, or C. 1. and then another C. 7E715C1C. To convert 4-bit groups to hexadecimal, you need to memorize all 16 4-bit patterns and their corresponding hexadecimal digit. This is rather more tedious than the 8 3-bit patterns of octal, especially since it is our instinct not to think of values higher than 9 as single symbols. The table in the diagram and repeated in the transcript will help. Consider these patterns to be vocabulary. And then finally, question number 4. Translate the following binary values to hexadecimal. So after some thought, what you should come up with is, for the first one, that's a 3. 1001 or 10 is an A. 1010. 1001 is 9. 1011 is 11 or B. 1110, 14 or E. 12 or C. 71101 is 13 or D. And then the second one translates to D, E, A, D, B, E, E, and then 1111 is 15, the highest possible value in hex, and that's an F. So the latter here, dead beef, is actually not just a joke. In some programs, it's deliberately copied into memory blocks as invalid initial data because it really stands out in a hexadecimal dump of memory during debugging. As with octal, ARM assembly lets you write an integer constant in hexadecimal, and you do this by preceding it with a pound sign, as we'll see in our example programs. In modern code, prefer hexadecimal. Octal is more common in code from the 1970s, and you'll find it still crops up now and then, especially in systems designed at that time, for instance in the representation of file permissions in the Unix operating system. And by the way, note that each byte in a binary pattern translates to 2 hexadecimal digits. It's remarkably easy to slide into thinking each hex digit represents a single byte, and to write, for instance, a 4-byte binary pattern using only 4 hex digits. Since each hex digit represents just 4 bits, you'd need 8 hex digits, not 4, for a 4-byte value. 4 bits, by the way, are sometimes called a nibble, spelled with a Y, which is a whimsical term for a small byte. It may sound silly, but it is the accepted term.